pull, pull. Now all of a sudden it starts moving. Let's keep it moving. It takes less force, and that's called a dynamic friction. And these equations that describe this force are given by a proportionality to how much the object is pushing down against the surface, how these forces, how these two objects are pressed together. This is called the force normal. Normal means perpendicular. So the more these are pushed together, the stronger the frictional force. If they're not pushed together at all, as they might be if they're just touching or in outer space, then of course the frictional force is less. There's another thing here, the constant proportionality mu. Mu depends upon the surfaces. It depends both upon this and upon this. For example, this might be dry snow, and this might be a ski. And then we have one type of mu. Then, after we've determined that mu, we have to look and say, how heavy is this guy? How much is he pushing down with his friction, with his normal force, in order to give a friction in this direction? Or with ice skates. And you can tell with metal, sharp metal on ice, or with a polished ski on snow, we're going to have a very, very small mu. But if we have sandpaper against a rough surface like concrete, then this is going to give us a tremendous value for mu between those surfaces, and therefore even a small normal force will be very hard to overcome the friction. We actually have to, in order to work those problems, we have to figure out what this normal force is. Well, normally, what is this? In this particular circumstance, it's going to be mg, because it's going to be the mass of this object here times the acceleration due to gravity, and that's the force of gravity. And so that's what it's going to be. But if we had an object that was sitting on an inclined plane, like this, then of course the force is going to be down this way, and it's going to have a certain component in this direction, and it's only that component of the force that's going to push them together. Obviously, if we tilt this almost all the way like this and put the object on the side, it's going to feel very little frictional force moving down. Why? Because they're not pushed together tightly. Therefore, there's very little normal force, even though we've got the same mu here. And so we'll be resolving these different forces and looking at problems involving frictional forces very shortly. So friction is one thing. Where does the friction arise? If we think of these atoms as bumps in the surface, it's irregularities in the surface and irregularities here, it's almost as though these bumps have to jog over each other like this. And it creates a lot of friction. And the friction goes into the form of heat. And so as we bump these molecules together, more and more, if they're rough, then we lose energy. And it's the loss of that energy that requires the force in order to keep the system going. Okay? Those are frictional forces. And our very important equation here is the force of friction is equal to mu times the force normal. This is the equation you must be familiar with. This mu here also can be mu static if the objects are not moving, or mu dynamic. So it can be either a static or a dynamic value. And those are relatively constant. In other words, if something goes faster, the dynamic mu does not change noticeably. So for any two surfaces, you're going to have a dynamic and a static value of mu. That enables you to look at how much the forces are pressed together and what your force of friction is going to be. The next force I want to look at is the elastic force called Hooke's law. This is the force that arises when we take something like a spring and we either stretch the spring out to some other point, by some distance x, or we could compress the spring where the mass was back here. It turns out that the elastic force is proportional to how much we distort it. And this is a very important equation because it holds true of all elastic media. If you just walk up to a wall and push on it, it will push back depending upon exactly in proportion to how far you have moved that wall. You say, well, I didn't move the wall. Well, you did a tiny bit. You compressed or you stretched it by some distance. And so this very important Hooke's law says that the force is equal to a constant times the amount you displace it from equilibrium. This is called the spring constant. Kind of similar to the mu that's up here. It's a constant of proportionality. And there's a negative sign here, meaning that if I push something from the resting point in the positive direction, the force is back in the negative direction. If I push it in the negative direction, then I'd have two negative signs and the force would be in the positive direction. So whichever I do, the spring tries to take the system back, the spring force, or Hooke's law, tries to take the system back to equilibrium. Now we'll use this a lot because you can see you could set up oscillating systems like pendulums are an example where we're using gravity or springs or any type of material. Even air can be a compressive material that vibrates when we press on it. The next law we want to look at is another kind of strange force. It's the centripetal force. The centripetal force is another one we're very familiar with. Just like we're familiar with friction, we're familiar with the spring force of elastic media, just like when you do exercises with a Bowflex or some type of pulling a bow back or any type of system that's being distorted, even like a rubber band. And the centripetal force you're very familiar with from driving around a corner. So as you go around a circle, then you find that there's a force that drives you to the outside and you must apply an equal and opposite force to stay centered, to stay on that circle. And that's what your car and the seat is doing. They're holding you, pushing you in this direction because normally you'd have a tendency to move outward. What is this centripetal force? This centripetal force is equal to the mass times the centripetal acceleration. And the centripetal acceleration is v squared divided by the radius. Didn't mean to hit the square there. And so if I go around a circle that has a radius r and I'm moving with a tangential velocity v, then the mass that's sitting on there that I'm moving around will feel a centripetal force like this. Let's quickly calculate a centripetal acceleration. Let's say we have a large circle here of 4 meters. We have a mass out here of 7 kilograms, and it's moving around that circle with a tangential velocity of 5 meters per second. First of all, can we calculate the centripetal acceleration? This is mass times centripetal acceleration. So the centripetal acceleration is going to be equal to v squared divided by r. And our v squared here is going to be 5, so this is going to be equal to 25 divided by our radius, which is 4. So it'll be 6.25. And that would be in meters per second squared. That's our centripetal acceleration. Now, if that centripetal acceleration is exerted on a mass of 7 kilograms, then our centripetal force is going to be 7 times as great, or 7 times mass times a centripetal. So it'd be 7 times 25 divided by 4. And that would be 175 divided by 4. And you can work that out. And that will give us our force in newtons that would be experienced by that mass that's going around that circle. We'll be working problems like this having to do with cars that are going around tracks racetracks and things of that nature. We'll look at cars going off on ramps where the ramps are tilted as they go out, how to balance the centripetal force with the force of gravity so that cars don't slide as much as they go around a circle, and problems of that nature. Finally, a very simple force, and that's the force of tension. This force of tension is equal to the force with which a rope is pulling. And so if you think about a rope, and you're pulling on this rope with a force of, say, 7 newtons, then there's a tension in the rope in both directions of 7 newtons. And it's important to say, okay, if 7 newtons is pulling this way, then each of these parts of the rope are pulling 7 newtons this way, and the forces being equal and opposite means that you're getting a force of 7 newtons in this direction, if everything is in equilibrium. So the force of tension is just simply the force with which this rope is pulling, or chain, or whatever the object might be. So this concept of tension. Force of tension, centripetal force, the Hooke's law force, or spring force as it's sometimes called, and the frictional force are 4 derivative forces that come, as we have here and here and here, from electromagnetic origins, and for the simple, and they come from the molecular structure of atoms pressing or pulling on one another. And here for the centripetal force, this is an artificial force that arises because of the rotational motion of something.